Welcome to Understand Chemistry. I am Dr. Bilal. In this video, I will talk about structure and reactivity of monomer and how it influences the nature of copolymerization. As we have previously learned, the Mayo-Lewis equation describes how two monomers copolymerize. It relates the instantaneous composition of the copolymer to the feed ratio of monomers and their reactivity ratios. The reactivity ratios of a monomer, denoted as R1 or R2, is defined as the ratio of the rate constant for self-propagation to the rate constant for cross-propagation. In other words, it tells us whether a growing radical prefers to add its own monomer or the other type. This reactivity ratio is a very useful tool to predict the type of copolymerization that will occur. But even more informative is the product R1-R2, which gives us insight into the overall behavior of the monomer pair. Let us look at few cases. If the product of R1 and R2 is equal to 1 and both R1 and R2 are close to 1, we get ideal or random copolymerization. If the product R1-R2 is equal to 1 but one ratio is greater than 1 and the other less than 1, we get known as a tropic copolymerization. If both R1 and R2 are 0, then product R1-R2 will be equal to 0 and we get a perfectly alternating copolymer. This means each radical only adds the other monomer. If the product R1-R2 is very small or almost 0, we still get alternating behavior but not perfectly. In another case, if both R1 and R2 are much greater than 1, then the product R1-R2 will also be greater than 1 and the system tends toward block copolymerization. This means each radical prefers its own monomer, but this is a rare case. Actually, in this case, we are most probably ended up in blend of two homopolymers. I have discussed these cases in more detail in my last video. So from this, we came to know that the reactivity ratio is a powerful parameter. It tells us what kind of copolymerization we can expect, but it does not explain why this happens. It does not account for the underlying chemistry, why one monomer prefers its own kind while another prefers the opposite. To understand the chemistry behind reactivity ratios, it is essential to look at the structure of the monomer themselves. Most vinyl monomers share a common structure, a carbon-carbon double bond with one substituent attached. It's this substituent, the group attached to the vinyl backbone, that make all the differences in how reactive a monomer is toward a growing radical. The reactivity of a monomer depends on several key factors. These are resonance stabilization, steric effects, and polar effects. Let's begin with the resonance stabilization, which plays a major role towards the reactivity of monomer or a radical. If the substituents on a monomer can delocalize the radical through resonance, it stabilizes the transition state and enhances reactivity. In other words, reactivity of monomer is determined by how well its substituents can stabilize the radical that forms during the reaction. For example, styrene has a phenyl group ring with delocalized pi electrons attached to the vinyl group. This allows the radical to be stabilized through resonance, making styrene one of the most reactive monomers in the radical polymerization. In fact, if we look at the order of substituents based on their ability to stabilize the radical through resonance, we see that groups like phenyl and vinyl are at the top, followed by electron withdrawing group like cyano and carbonyl, and finally simple alkyl or hydrogen substituents. Besides understanding the reactivity of monomer, the reactivity of radical is also important. The reactivity of radical is inversely related to the reactivity of a monomer. The order of substituents present in the radical in increasing order of reactivity toward monomer is exactly opposite from the order of substituent present in monomer. So from the reactivity order, we can see that the same substituent that makes a monomer more reactive towards radicals also make the corresponding radical less reactive. This inverse relationship is key to understanding copolymerization behavior. Let us understand with the help of example from this table. If we see the relative reactivity of monomer toward polymer radical, we can see that the monomer styrene is highly reactive toward vinyl chloride, as the relative reactivity of styrene toward radical is 50. On the contrary, the reactivity of vinyl chloride toward styrene radical is very small, as the styrene radical is resonance stabilized as shown here. The interaction of radical reactivity and monomer reactivity in determining the rate of a radical monomer reaction can be more clearly seen by the use of the reaction coordinate diagram. The diagram shows the potential energy changes associated with the radical monomer reaction as a function of the separation between the atoms forming the new bond. In the diagram, the S in MS and RS indicates presence of substituents capable of resonance stabilization. However, M and R means monomer and radicals that contain simple substituents that cannot show resonance stabilization. Methacrylate is the monomer that contains simple substituent, whereas styrene is the example of monomer that contains substituent which is capable of resonance stabilization. Similarly, vinyl acetate radical and styrene radical is example of R and RS respectively. There are two sets of potential energy plot in this figure. One set of 4 repulsion plots that show the energy barrier due to steric hindrance or electronic repulsion when the radical gets too close. The other set of 2 Morse plots show how potential energy changes as the radical approaches the monomer. It represents the stability of the bond finally formed. These energy changes are shown for the 4 possible reactions between resonance stabilized and non-stabilized monomers and radicals. The various activation energies EA and heats of reaction delta H are represented by the solid line and broken line arrow respectively. The 4 colored intersections in the diagram mark the transition state for 4 possible reactions. Reaction A corresponds to intersection highlighted in blue. This is a standard radical reacting with a regular monomer. It has a moderate activation energy and is relatively fast. Reaction B corresponds to intersection highlighted in green. Here, a standard radical reacts with a substituted monomer. The resonance stabilization of MS lowers the activation energy, making this the fastest reaction. Reaction C corresponds to intersection highlighted in orange. Here a substituted radical reacts with a regular monomer. The radical is stabilized, so it's less reactive, and the monomer is not activated. This leads to higher activation energy and slower kinetics. Reaction D corresponds to intersection highlighted in red. In this case, both radical and monomer are substituted. While MS helps slightly, the overall reactivity is still low due to steric hindrance and radical stability. Now, the order of reaction rate constant is shown here. This means reaction C is the slowest and the reaction B is the fastest. Why this order? Actually, it is a balance of 2 factors. Radical reactivity. R is more reactive than RS because it is less stabilized. The other factor is monomer activation. Here MS is more reactive than M due to resonance effect. So the fastest reaction combine a reactive radical with an activated monomer, MS, while the slowest combine a stabilized radical, RS, with a regular monomer. So we see that structure of the monomer, especially when it has a stabilizing substituent, influences both self-propagation and copolymerization efficiency. Let's start with self-propagation. Monomer without stabilizing substituents like vinyl acetate or vinyl chloride tend to propagate quickly. Their radicals are reactive and readily add more of the same monomer. In contrast, monomers with stabilizing substituents like styrene form radicals that are resonance stabilized and therefore less reactive. So their self-propagation is much slower. Now, what happens in copolymerization? If both monomers are either stabilized or unstabilized, like styrene with acrylonitrile or vinyl acetate with vinyl chloride, copolymerization can proceed. But if one monomer is stabilized and the other is not, like styrene and vinyl acetate, the reaction becomes inefficient. Why? Because the styrene radical being stabilized react very slowly with vinyl acetate. This reaction indicated by equation C in the last slide. Meanwhile, the vinyl acetate radical, being reactive, quickly adds styrene indicated by equation D in the previous slide. This imbalance leads to poor incorporation of vinyl acetate and irregular copolymer structure. So even though the reactivity ratio might suggest alternating behavior, the actual chemistry, the radical stability and monomer structure determines whether copolymerization is efficient or not. Now let us move on to another important structural factor, the steric effect. This describes how the position and number of substituents on a monomer influence the reactivity. When the substituent is at the alpha position, it tends to have an additive effect, making the monomer more reactive. But when substituents are at the beta position, they cause steric hindrance, which make the monomer less reactive. Let us see how substituents affect monomer reactivity using this comparative table of rate constants. We are looking at a series of chlorinated ethylene monomers and we'll see how they react with different polymer radicals, vinyl acetate, styrene, and acrylonitrile. The key idea is to see how the number and position of substituents influence the reaction rate. Let's start with the vinyl chloride, which has one chlorine at the alpha position. It serves as a reference point. Now, compare it to vinylidene chloride, which has two alpha substituents. Its reactivity is more than twice as high, showing the additive effect of alpha position. Next, look at cis-1,2-dichloroethylene, where both chlorines are at the beta position. Its reactivity drops more than 20 times compared to vinyl chloride. That's due to steric hindrance. The radical struggles to approach the monomer. Trans-1,2-dichloroethylene is a bit better. It's about 6 times more reactive than the cis form. The trans configuration reduces steric clash, but the beta substitution still limit reactivity. Then we have a trichloroethylene. With 3 substituents, it's less reactive than the vinylidene chloride, but more reactive than the dichloroethylenes, showing that position matters more than just the number. Finally, tetrachloroethylene with 4 bulky substituents is the least reactive, almost 70 times less than vinylidene chloride. This confirms that excessive substitution near the double bond severely hinders polymerization. There's also an interesting exception. Polyfluoroethylene, like tetrafluoroethylene, show enhanced reactivity despite having multiple substituents. That's because fluorine is small and its steric effect is minimal. Now let's look at the third major factor influencing monomer reactivity, the polar effect. This effect depends on the polarity of double bond, the nature of the substituents, whether it is an electron donor or electron acceptor. Most vinyl monomers have a structure like this: a carbon-carbon double bond with a substituent attached. This substituent determines whether the monomer is electron-rich or electron-deficient. Let's start with electron withdrawing substituents, also called acceptors. These include groups like chlorine, as in vinyl chloride and vinylidene chloride, cyano group, as in acrylonitrile, or carbonyl groups, as in methyl vinyl ketone or vinyl acetate. These monomers are polarized with partial positive charge on the double bond carbon that make them more reactive toward electron-rich radicals, especially those with the donating groups. On the other side, we have monomer with electron-donating substituents like alkoxy chains, as in vinyl ethers, phenyl rings, like in styrene, and conjugated systems, as in butadiene. These monomers are electron-rich, and they prefer to react with electron-deficient radicals. So the polar effect helps explain selectivity in copolymerization. A radical with an electron-donating groups will favor monomer with electron-withdrawing substituents, and vice versa. Together, these three effects, resonance, steric, and polar, give us a complete picture of monomer activity in radical polymerization. Let us now connect the polar effect to actual polymer behavior. This slide shows how the difference in polarity between monomers influence the type of copolymer formed. The key idea is the greater the polarity difference between two monomers, the stronger the tendency towards the alternation. Let's look at two examples. First, acrylonitrile and methyl vinyl ketone. Both monomers have electron withdrawing substituents. Acrylonitrile has a cyano group and a methyl vinyl ketone has a carbonyl group. Because their polarity is similar, the product of their reactivity ratio R1-R2 is close to 1. This leads to random copolymerization. Now compare that to acrylonitrile and 1,3-butadiene. Acrylonitrile is strongly electron withdrawing, while butadiene is electron donating. Due to its conjugated diene system, this creates a large polarity difference, and the product R1 into R2 is very small, around 0.06. Such a low value indicates strong alternating copolymerization, where each radical prefers the opposite monomer. So in summary, small polarity difference leads to random copolymer, while the large polarity difference leads to alternating copolymer. I hope you now understand how resonance, steric, and polar effect govern monomer reactivity in copolymerization. If you have any question or need clarification, please feel free to ask. Thanks for watching.